So coming to optimization of echo 2D echo images. So this is the screen which we get when we turn on the 2D echo. So all these uh, were explained earlier. The This is the soft menu and all this is. So we'll go into all these functions in detail. So first is the grayscale map. When we talk about 2D echo, we have the option of changing various grayscale maps. So what are these grayscale maps? Is the manufacturer has put in various maps, that is various shades of gray, and they have prepared various maps, that is map A, map F, like that. So each map will have various shades of this gray, and based on our preference, we can choose which map we want. So this is an example that will show the difference between grayscale map F or map A. So this is the video image showing the difference between the various. So you can see that there is a difference in the shade of this grays as well as the shade of this. So it's our preference and to choose which grayscale map we can use. The importance, why do we need more maps, grayscale maps like this, is that maybe if we change the maps, we can detect various uh, structures which are not visualized. Let's say, for example, an LV thrombus or a small thrombus sitting here and all. If we change the map, sometimes this thrombus may become very evident because it is having a different shade of gray and it may become evident. And various like similarly various structures we can be made out clearly when we change the map. So generally we go with the default map only, but in certain scenarios we may have when we are suspecting something more like a thrombus, or we are suspecting a more on the vegetation on the aortic valve, suppose if it's a vegetation or not, we can try changing the grayscale map and look for more details, like, and it may appear more evident when we change the map. Coming to the frequency, already explained. Our range of frequency is 3 to 5. We have a low frequency probe with a deeper penetration. So the higher the frequency, less the penetration, and we get a better contrast image. So ideally, we have to target for a higher frequency. Why? Because we get the more image resolution and contrast with the higher frequency. Uh, and but if the penetration is adequate with the maximum available frequency, then we can continue with that higher frequency itself. But if it's not penetrating enough, then you will have to bring down the frequency and so this is an image showing static image, showing low frequency setting and this is a high frequency setting. With a high frequency, you can see that this resolution is much better, more clear than this. It is more hazy, whereas this resolution is much better. So that is the difference when we go for a high frequency. To target a high frequency, and this is a cine image showing difference in a low frequency as well as a high frequency. You can see the clarity is more with the high frequency compared to this. So this is a high, this is a low frequency. So like that we can optimize our image by changing the frequency in 2D mode. This is another static image. 5 frequency, 5 megahertz is having a better resolution than a 3 megahertz. Next is coming to dynamic range. This is a common setting we always see on the probe but not knowing what it is. So dynamic range refers to it will adjust the appearance of the shades of gray on the image actually. That is, when we put the dynamic range, it's a value in decibels. You can rotate the knob and change the dynamic range. The optimum is 70 to 75 decibels. When you reduce the dynamic range, that is low dynamic range, it will show less shades of gray. That is, it will becoming more of like black and white, and more of the shades will disappear. Whereas if you increase the high dynamic range, you will get more shades of gray. More shades are coming. So uh, uh, in this example, this is a low dynamic range. Here with the kept dynamic range kept at 50, this is more black and white, and here more grays are not coming. It is appearing like a black and white more of. But what happens when you increase the dynamic range to 75, the shades of gray are appearing more, and you are able to see more structures. So same for looking for LV thrombus or LV non-compaction. If you increase the dynamic range, you can see more structures more clearly and better. So this is a video cine image showing the dynamic range. This is with low dynamic range, whereas this is with high dynamic range. You can see more structures are clean clearly with this, whereas this is more of a black and white image with low dynamic range. So that is how dynamic range will affect your image quality. Same static picture. So low level of dynamic range, this is the optimal level. So when it's cine image, you can change the dynamic range and according to your preference, how it is viewing better or not, you can put that dynamic range and continue with this. Next is coming to power. Power is like the strength of the ultrasound signal which you are giving from the ultrasound probe. So it is expressed in decibels, and the power, it is like whether you are using the maximum power or not. And the power setting is limited by the FDA approval because based on certain standards. So we are not supposed to use, the manufacturers are not supposed to put power beyond their rated limit into their machines. So it is always better that we use the maximum, utilize the maximum power, and it will be generally safe. And that safety is based on that mechanical index and thermal index, which we have briefly talked about in this thing, which we'll talk later. So power is shown here like 0 here on this thing, and which we can adjust here. That is in the soft menu, we can go to this power and adjust the power, keep it at the maximum, no issue, provided the mechanical index and thermal index are within the limits. So the power will control the amount of acoustic power applied in all the modes. In all modes, the power, I think the same applies for Doppler or any this thing, Doppler or color Doppler or M mode, everything the power, it's one setting. For all modes, it is the same. And when it is set to maximum, it is equal to or less than the maximum acoustic power permitted by the FDA. So keep the power maximum. When the power is reduced, the image will become more noisier. So keep it the maximum. Coming to mechanical index, why is it called mechanical? That is, it denotes the extent of mechanical damage these ultrasound waves can cause to the tissue. So mechanical index is shown on the screen on the top right hand corner, MI.4. So that is the mechanical index, and the TIS is the thermal index. SO is for soft tissue. So for various tissues, they'll show various abbreviations. So we are talking about mechanical index now, MI.4. So it is an attempt to measure part of an ultrasound beam's bioeffects inversely proportional to the frequency. Higher frequencies will have a lower mechanical index, and it is an indication of an ultrasound beam ability to cause cavitation related bioeffects, and is currently thought to be a reasonable proxy for micromechanical damage. Generally, ultrasound is safe, but still to measure any bio effect or damage these beams can occur, we use this mechanical index. So the FDA mandates that it should be kept below 1.9, and it doesn't have a unit. Complex equation is there to calculate, and all this we need not go into details. So what is the importance of mechanical index in our cardiac echo is that when we are doing contrast echo, it is of importance, and uh, the relationship between frequency and cavitation is the different bubble size are susceptible to cavitation at different frequencies. So two different ultrasound frequencies cavitate bubbles of different sizes. So this concept will come when we discuss about contrast echo. So we have to reduce the mechanical index when you're doing contrast echo, I suppose. So low mechanical index, high frequency, low pressure, linear behavior, no cavitation, no harmonics. So when we are doing harmonic imaging, which will come into details later, we have to keep a high mechanical index. Now coming to thermal index is that how much the tissue can get heated up by these ultrasound waves. So thermal bioeffects. So it is often displayed on ultrasound screen, which I showed it, TIS. So it depends on the acoustic power, the tissue which is being heated or which the tissue which is being imaged, and the path of that ultrasound beam. So the clinical relevance in cardiac, we need not bother about the thermal index because heart never gets heated up that quickly when you are doing. But this thermal index comes of significance when they are doing fetal echo or when we are doing embryo ultrasound and all, because uh, there it can play a significant role. So we have to bother about the thermal index when we are doing a fetal echo or something. So TIS, thermal index, X stands for soft tissue, TISB stands for bone, and TIC stands for the cranial bone. So various, based on the part which you're scanning, it will come TIS, B or C like that on the echo machine. Now important, another aspect we have to see about the sector size. Sector sizes, that is the area, this is the sector. So like a pie shape. So that size is important because it will affect the frame rate. So wider sector size decreases the frame rate. That is, the more bigger and wider you keep the sector, it is not good. It will decrease the frame rate, and when the frame rate decreases, it will decrease the temporal resolution. So when we are scanning a fast moving structure like a valve, the valve movement, aortic valve, you should typically decrease the sector size. So this is comparing image showing how the sector size is affecting, how the sector size is affecting. So we had also note that the depth also will affect. So with the wider sector width, the frame rate is 43 at 240 mm depth. Here at 240 mm, same, the frame rate is 73. And here we are getting a higher frame rate when we are reducing the sectors width to less. So the frame rate is improving. You are getting a better frame rate. So reduce the sector size, get a better frame rate. So this is a cine image that will show better frame rate with at of 83 hertz. This is showing a frame rate of less, 73 only, and when the sector size is increasing, it is showing a very this thing. So this is more good resolution, better, clear than these two. Now coming to the sector depth. So whenever you put a probe, there will be you after the heart, if there is unwanted space here, this much depth is not required. So you better reduce the depth, because reduce the depth and increase the frequency. So when we reduce the depth, it becomes more clear and all. So this is a static image showing this is an unwanted depth. 210 depth is not required. This is the optimal depth. So we'll see a cine image how depth is affecting. So better resolution and better more structures are visible. Here dynamic range is more, so we are seeing more of this, but the structures are not seen here. Now coming to focus. Focus is like when we are seeing a Planck's view, we can focus, if we are focusing on the mitral valve or the aortic valve, there is a focus point marker which we can focus it towards that particular valve, and at that point the transducer will focus more and will give a better resolution compared, like how the phased array focuses on that, which the mechanism which we had seen earlier in the phase array, okay, how the steering as well as the focusing, that picture we had seen. So likewise, so this is how it will focus on thing. So that resolution will be increased. So this is the focus marker which I told you. So this we can increase or decrease. So when we decrease it and bring it to this level, that area will be more focused. So we are bringing down it and we are able to focus that. So there will be, see, the valve leaflets are more this thing, and we decrease the focus point there. So this is another static image. So you can have one focus line or can have two focus line. So this is a two focus line range of focus. So this thing we are bringing it down here because we want to focus on this area, trying to see the pulmonary veins entering into the LA. So here we can see more. Here the focus point is here, whereas in this image we are bringing it more down. So we are able to see more when the focus point is near the mitral valve. Here it is brought down, whereas here the focal is more on top. We are able to see more clearly at the valve annulus and the valve leaflet, and this area also we are able to see more clearly compared to this image. So that is the use of a focus point. So how does it do? We had already seen the phased array focusing at a particular point. That is they fire at after a specific interval time. Initially this is fired, then this is fired simultaneously, then that. Likewise, the beam is focused into a particular point. Now coming to overall gain. Overall gain is generally the brightness of the image. So there is two types of gain. That is the overall gain as well as the TGC, time gain compensation. Overall gain, the brightness of the image we can increase. That is, if you press auto gain button, it will automatically adjust the overall brightness according to the scenario. And after, if the auto gain also it's not satisfying, then you can manually increase overall gain. So that is also expressed in decibels. So here we can see gain is 4 decibels. Here gain is only 0. So as an image of that, this is suboptimal gain, whereas here we are getting more better gain and able to see more clearly. What is time gain compensation? TGC, this knobs you must have seen already in your echo machine. So this is gain increased based on the area on the screen. That is, this if you increase this, it will increase the gain on the upper part of the screen. This will increase on the lower part of the screen. I should say it's on the upper part of the areas. So in the field. So this is for the near field and this is for the far field. So optimum, this is the optimum how you should, because why? Because when the ultrasound is passing through the tissue, initially when it goes deeper and deeper, it is natural that the ultrasound waves in amplitude decreases as it goes deeper and deeper. So when it goes deeper and deeper, it becomes more darker and darker. So typically, to compensate that it is getting darker and darker at the deeper areas, you have to increase the gain. So at the near field, whereas you need not increase because it is of good intensity here. As it goes down, it is getting darker, so you have to compensate that by increase the far field gain more compared to the near field. So this is the optimum setting which they say, but typically when we image, we just have to manipulate even the near field also a little more to get. So it is our personal preference, and based on what we see, we can adjust according to that. So this is a normal gain. Here the gain is too much and gain is too low. This overall gain actually. So this is how the TGC, the upper near field is kept too dark here. Here the near field is get too bright here. So both. So TGC, why is it called a time gain compensation? And this compensation, we know that it is compensating because it is going more deeper and deeper. Gain, we are adjusting again, time gain. So why is it called time? In ultrasound, depth is synonymous with time because the ultrasound machine calculates the depth of the structure based on how long it takes for the ultrasound to reflect back and return to the transducer. So that is why it is called time gain transducer. It would have been much easier to understand if we say it as depth gain compensation, but the manufacturers has termed it as TGC or time gain compensation. So that is how this terminology comes, time gain compensation. Time is synonymous with depth and it is compensating for the more darker it is getting deeper into the tissue. So now coming to zoom. Zoom, already everybody will be knowing, like when we zoom a picture, generally when we zoom a picture, if you go very high zoom, that resolution will become low and the image will be blurred. Suppose we are in this crowd, we are zooming into this person's face, we may not be able to see it more clearly because the resolution of the entire picture is low. But in echo, the advantage is the resolution is very good, and even if you magnify or even if you zoom it, it will not affect the resolution. So even if you zoom it, you see it still more clearly, and so therefore you can use zoom very liberally in this thing. If you want to see a valve agitation or something, you can use it liberally and zoom it. So this is how zoom works. This particular area you're zooming in, and you're seeing more of this area in this is the LVOT view. Zooming in more into the LVOT view without any change in the resolution. Actually, the resolution and the uh, structures are seen more distinctly and clearly. Now coming to frame rate. Frame rate is the number of frames per second. So more the frame rate, more the resolution. So in 1 second. So this is 60 fps means 60 frames per second. So image produced per unit time. Higher the frame rate, higher the temporal resolution. So temporal resolution ability to see is moving points. Moving points. Coming to compression. Compression will affect the image contrast. Why? Because in a normal ultrasound wave, if we plot it on a graph like this, there are alternating areas of compression and rarefaction. So at the areas of compression, we get more darker. So the more you compress, the more gray shades will come together, and therefore, if you this compression value will affect the contrast. So if there is a knob for compression, the setting you can change for compression. So if you if you increase the compression, more the compression, more the contrast. That is how compression works, like. And rejection, this is another setting in optimization. Rejection, that is, we can there will be so many low velocity reflected frequencies that are reflected from unwanted areas when we perform an echo. So these low level echoes can be eliminated by rejection, and this will be eliminated and these areas will appear darker. So that is we call rejection. And if we see more noise, we can increase the rejection value more, and therefore these noises will be eliminated. That is why we call rejection. Next is contour. This is also a soft setting we can change. Contour generally means the border. That is the border. That is a word meaning of contour. Like in a mountain, there are various contour. Like this is for beauty, contouring and highlighting, like for facial this thing and all. So generally contour means the edge enhancement. That is the extent of edge enhancement. That is when we are trying to trace the image, if we put that contour and trace its setting, we can get a more edge detection, and that edge can be traced more this thing, and contour can be seen more clearly when we put on that function. So that is contour. Next is B mode colorization. That is generally we see it as a black and white image or a gray shade. But if we apply a sepia, a color over that, certain structures can be seen more clearly. So in certain scenarios, we can apply a B mode colorization, and we can apply a single uniform color over that, and that color will show over that, and we can see some structures clearly. So the sepia map varies, different colors, green, etc. will come. So we can choose accordingly. So that is the B mode colorization. So this is the difference between the cine image showing the different colorization, B mode colorization, and various colors we can choose. Next is coming to harmonic imaging. So harmonic imaging, we know the harmonium, and uh, this principle, the harmonic imaging, we have to know. Generally, when we send in an ultrasound image, the tissue will reflect and will send back an image. But at times, the image on the tissue on which this ultrasound beam strikes, sometimes the tissue itself will generate a sound wave that is different from the sound we have sent in. That is, the sound which you have sent in is called the fundamental wave, fundamental frequency, and the tissue by itself will generate a frequency to start with the higher frequency from that tissue, and it will send back. So based on this principle, we can get a more clear image. So that is, the tissue also will generate a sound wave. So based on that, there is this thing called the harmonic imaging. So the sound wave which is generated by the tissue itself can be detected by the probe, but what we have to do is we have to eliminate the fundamental, the frequency which we have sent in, and that also will reflect back. So that we have to eliminate, and we have to take in only what the tissue is this thing. So the tissue is generating this frequency because of this fundamental frequency is striking on that. So, and that new frequency is generated in integral multiples of the fundamental frequency. And this we typically use in contrast echo. So at the site of entry of this fundamental frequency into the tissue, a high frequency sound wave is generated by the tissue, and at the deeper within it, that will that amplitude, the strength of that signal is maximum at the 4 to 8 centimeter within the chest wall. So this, with this picture, suppose we are sending a fundamental frequency through the chest wall, so that as it goes deeper and deeper, the amplitude decreases. But this harmonic uh, signal is generated by the tissue, and it is starting from deep within and it is coming towards the transducer. So at the deepest area, that is typically within 4 to 8 centimeter, will have the best high frequency harmonic image, and as it comes towards the transducer, it will come decrease in amplitude. So that is a basics of harmonic imaging. So it will come in multiples, that is first harmonic, second harmonic, like that. So based on this principle only, this music instruments, harmonic instrument and all works. It is in multiples of this fundamental frequency. So like I said, we have to get the sound wave generated by the tissue. We have to eliminate the fundamental frequency. So the ultrasound machine does this by two ways. That is, it will either use a filter and filter off the fundamental frequency. The other method is a pulse inversion. That is, uh, this is the fundamental frequency which the probe is sending into the tissue, and when it strikes the tissue, it will generate the harmonic frequency. So this is in phase. Now, when we make it out of phase, this will eliminate the fundamental frequency, and only the harmonic, amplified harmonic signal will be remaining. So this is called pulse inversion, and based on this technique, we can eliminate the fundamental frequency. So that is just the basic of harmonic imaging. The harmonic imaging advantages, we can get more clearer uh, pictures. So this is a static image showing fundamental height. Normally without harmonic we are using, and this is with the harmonic image. This thing, we are getting more details of the valves, the particulars of the image are more clear in this. It's an image showing normal, for normal imaging versus a harmonic imaging. Next we will discuss about Doppler and optimization of Doppler settings.